It is my pleasure to welcome you here to this webinar today. Do appreciate you taking time out of your schedules to meet with us. As Keith pointed out, we'll try to keep this today to about 30 to 40 minutes, and we'll allow some time at the close for some question and answering. And as Keith already pointed out, the title for today's webinar is Infrared Camera Measurement and Microscopy, Measuring Temperature at the Micron Level. The agenda that I've prepared for today's webinar is as follows. First, I will review how thermocouples perform temperature on small targets. I will also describe how IR or infrared thermometers or spot pyrometers perform when measuring on small targets. We'll then contrast and compare that to infrared cameras and how they measure and image small targets. More specifically, we'll define the different spatial resolution properties. So we have an understanding of what those terms and what those different parameters are. I will then take you through some spatial resolution calculations to show how you can calculate whether or not you're acquiring enough information with the infrared camera to accurately report temperature information. I will then perform a comparison of images and measurements from various infrared systems, looking at different target sizes. And then we'll spend a little time talking about optics. What is available out there today for doing microscopy or close-up work with an infrared camera? And then we'll wrap up with some summary and conclusions, and then, of course, some time available for question and answer. So first of all, let's talk a little bit about thermocouples and small targets. There are some limitations associated with thermocouple legacy technology. In a previous webinar, we talked very specifically about thermocouples and contrasted and compared those to infrared camera measurements. And if you weren't able to participate in that webinar, it is available for playback. To summarize what the limitations are for thermocouples, first of all, contact is required with the target of interest when utilizing a thermocouple. And we learned in our previous webinar, focused on thermocouples, that in order to measure surface temperatures, permanent adhesion to that target is required. Otherwise, we learned that we don't get good contact, which means we don't make good measurement. So permanent contact is required in order to make accurate surface temperature measurements. We learned also that when we make contact with a target of interest, that the thermocouple indeed becomes a heat sink, drawing heat away from the target of interest. And that's okay. That's what a thermocouple is designed to do. The problems start to present themselves when our targets of interest become small in size and they have very small thermal mass. In those situations, we see that we draw too much heat from the target of interest, and we adversely affect the thermal properties of the target. And finally, of course, some targets are so small that the thermocouple becomes too large that we cannot apply the thermocouple to that target of interest. They're just size limited. Now, more specifically, let's address this concept of the thermocouple acting as a heat sink. I have an example here of a bridge where a thermocouple is attached to this thermal bridge. If we look at this target close up, we see that the thermocouple is acting as it should, being a heat sink, but because our target is so small and because the thermal mass of our target is so small, we're pulling so much heat from it that we're adversely affecting the target of interest. In a sense, we're actually cooling this bridge. And so the resultant measurement with our thermocouple is erroneous. Let's review now infrared thermometers, or sometimes called spot pyrometers, and small targets. What are some of the limitations here? Well, we, in a previous webinar, talked more specifically about IR thermometers and how they perform when compared to infrared cameras. And again, that webinar is available for playback. But what we learned in that webinar was that IR thermometers, while they have an input parameter for emissivity, they do not have an input for the reflected temperature, which reflected temperature and the emissivity parameters are both parameters that are utilized to calculate temperature accurately with an infrared device. We learned from that webinar and from the experiments discussed in that webinar that not having a reflected temperature input is an inherent limitation to IR thermometers and does result in a percentage of error in IR thermometer measurements. We also learned in that webinar, when we are looking at very small targets, that it is very difficult to know exactly where we are measuring with our IR thermometer. There are target alignment challenges. We also learned in that webinar that there are size limits that we can measure with the IR thermometer. In fact, we utilized in that webinar a special IR thermometer. That was not cheap. It was actually a $1,000 spot pyrometer or thermometer that had in it a close-up capability. But even with that close-up capability, we were limited to a spot size of roughly 5 millimeters by 5 millimeters. And at that spot size, we noticed that we had greater than 3 degrees centigrade temperature variation. So anything smaller than that, we just couldn't measure with this specialized IR thermometer. With typical IR thermometers, our threshold was more at 25 by 25 millimeters. So there are size limitations associated with these IR thermometers. And let's review that in just a little more detail. First of all IR thermometers have what's called a distance to spot ratio, and the ratio will give you the minimum target area for measurement. And of key importance when utilizing IR thermometers, of key importance is to ensure that the target of interest is larger than that spot size, because what happens is the IR thermometer actually measures an area and not necessarily a spot. When you see the lasers coming off of most spot pyrometers, those are typically there to give you an indication or an idea of where your area is centered. Some of the more advanced thermometers will actually create an area, a circular area, to indicate the area that you're averaging. And it's important and critical to keep in mind that it is that entire area that is averaged as a part of that measurement. Now here's just a real quick example of how we can utilize the DS ratio, or distance to spot ratio, to determine how much area we're averaging. And we'll see how this translates over to the infrared camera measurements and spot sizes. In this example, I have an IR thermometer that has a distance to spot ratio of 30:1, which means if I have a target at 30 inches distance from my IR thermometer, the area averaged is 1 inch. Or, for example, if I'm at 60 inches from my target, the area average becomes 2 inches. It's a 30:1 ratio. Very simple to use. Okay, now let's dive into the infrared camera and how we can utilize it to measure small target sizes. But first of all, let's just review briefly how the infrared camera works. This will help us understand what we can and cannot measure or see with the camera. Again, the camera has within it a focal plane array. It is an array of sensors or detector elements. In this particular example, I'm referencing the FLIR T420. And the T420 is an instrument that is available from Technitool as one of their benchtop test kits. The T420 has a 320 by 240 detector array, or over 76,000 pixel elements. Now, each one of these elements senses infrared radiation. It converts that radiation to a temperature value through a calibration process. The temperature values are assigned a color or grayscale and then presented as an infrared image. Understanding that my infrared image is made up of several thousand individual spot measurements, it's easy to understand how I can use analysis tools on the camera or in software on the imagery to extract temperature information. And I can use analysis tools like an area tool to extract the maximum, minimum, or average temperatures, or I can use tools like spot tools and extract the single spot temperature value. When you think about it, having all of these measurement values available, it's like having over 76,000 thermometers, IR thermometers, or thermocouples to measure my target. Let's review briefly some of the parameters surrounding spatial resolution. There are essentially two types of resolution that we talk about when we talk of infrared cameras. We talk of thermal or temperature resolution, which usually indicates what are my temperature ranges, what is the sensitivity of the camera, what is the accuracy of the camera. We also talk about spatial resolution, and spatial resolution tells me how much will I capture with my image and how small or how detailed can I measure with my image. And here are some pretty typical parameters and definitions. First of all, field of view. The field of view is essentially what the camera sees at a given distance. What will my resultant image be? There is horizontal field of view and vertical field of view. The vertical field of view is essentially what do I see in the vertical aspect, whereas the horizontal field of view is what I see in the horizontal view or aspect. Another parameter that you may hear from time to time is the pixel pitch. The pixel pitch is the size of the detector or pixel. And what I have displayed here is a microscopic image of a microbolometer detector. This is the detector that is in the E40 and T420 camera that's available from Technitool. These cameras have a pixel pitch of 25 micron. Some additional spatial resolution terms are instantaneous field of view. And the instantaneous field of view, or IFOV, is the solid angle that is subtended by a single pixel. And sometimes you hear us talk about degrees and millimeters on focal lengths. The IFOV is described as milliradians. And this will make sense as we get into some of the calculations that are coming up shortly. The spot size is the more important parameter to understand. The spot size is defined as what a single detector or a pixel element will see at a given distance. And there's a very simple formula that we can utilize to determine the spot size. We just used some simple math to determine the spot size for an IR thermometer. You remember we had the 30-to-1 distance to spot ratio. In this example, we use the instantaneous field of view multiply that by the distance to the target, and that will give us the spot size of an individual pixel. So let's discuss this in more detail. Let's discuss what it means to determine the spot size. And I have an example here of a printed circuit board. And I've overlaid on top of that image a grid work that represents the individual pixels. And let's say that my target of interest is one of these very small leads. I want to measure the temperature of one of these small leads. Now, remember, just like the infrared thermometer, it was so important that my target was larger than the spot size. And the same is true for an infrared camera. In fact, if the target is smaller than the spot size, that target will be averaged over a single pixel. And if it's averaged, I may not even see it with the infrared camera. I most certainly will not be able to measure it. So when it comes to spot size and measurements, we recommend that you capture a target with a 3 by 3 pixel grid. And if I have a 3 by 3 pixel grid capturing my target of interest, I'm guaranteed I will have at least one pixel fall squarely on my target of interest. And I've shown that here where we've zoomed in on one of our leads that we're interested in measuring. And if we look at a 3 by 3 cell, at least one pixel element falls squarely on the target of interest. And sometimes you may hear this called a measurement spot size or a measurement cell or a measurement grid. So let's do some examples. Let's crunch some math and see how this works. In this particular example, I want to know how many pixels will capture a target, and this target is 3.5 millimeters by 2 millimeters with an E40 camera and a 45-degree lens. And let's say that I'm at a distance from my target of 0.4 meters. So I know from my formula of distance multiplying that by the instantaneous field of view that I'll get my spot size. I can do that math. And when I do that math, I determine that my spot size for my E40 and lens combination at that distance, I know that my spot size equals 2 millimeters. So how many pixels do I capture at that distance? Well, in the vertical view, I capture 1.7 pixels, and in the horizontal view, I capture 0.97 pixels. So I don't even capture the target with a single pixel at that distance with that lens. And here is displayed the thermal image captured with the E40 and that lens combination and the resultant temperature measurement. I've used an area tool, and I'm displaying the maximum temperature, which is 45.8 degrees C. What's happening in this particular instance is I'm averaging on the pixels in the horizontal view or aspect. In the vertical aspect, I may be positioned squarely on a pixel or a target. I'm not sure. All right, here's another example. And in this example, I'm utilizing a T420 and a 45-degree lens. And my target is the same target. It's a very small IC integrated chip that is, again, in measurement, 3.5 millimeters by 2.0 millimeters. And let's crunch the math, and the formula stays the same. My distance is the same of 0.4 meters or 400 millimeters. My IFOV, though, changes. It becomes 2.59 in this instance. So my spot size now is smaller. It's 1.0 millimeters. So my spot size now with this camera and lens configuration is much smaller. And let's display the number of pixels. Oops, sorry about that. So the number of pixels I have in the vertical aspect are 3.38 pixels. Oh, and in the horizontal, in the horizontal I have 1.93 pixels. So 3.38 and 1.93. Not sure why that horizontal is displaying. But my temperature value here from the thermal image measures 46.4 degrees C. So it's actually warmer when measured with the T420 and that 45-degree lens. And the reason why is because I'm capturing more pixels. I'm closer to having that 3 by 3 grid for measurement. Now, just for giggles, if you will, I thought I would take the most advanced infrared camera that FLIR has available today and compare that to the measurements we just made with the E40 and the T420. And this is an SC8300. And the SC8300 is a HD camera. It has 1344 by 784 pixels. So it's a megapixel camera. And this camera, let's say that we have a 25-degree lens on it, and we're at that 0.4 meters distance. Well, how does the spot size compare to this camera? The distance, again, is still 0.4 or 400 millimeters. My instantaneous field of view is 0.56. So I multiply those two parameters, and I see that my spot size now becomes very small, 0.2 millimeters. And in the image, you can visibly see the difference from the previous images. And that's because I have more pixels, and my spot size is a lot smaller. Nope. Must be having some kind of technical issue here. Let's see. Let's see what the number of pixels are. In the vertical aspect, I have 15.63 pixels falling on my target. In the horizontal, I have 8.93 pixels falling on my target. And you can see that my maximum temperature value has gone up even further, even more than before. And again, the reason why is now I have more than a 3 by 3 grid on my target of interest. And I have at least one pixel falling squarely on my target of interest. And the maximum temperature is being more accurately reported at 48.8 degrees C. Okay. The next slide here is a comparative of our printed circuit board target taken with these different instruments. The first image is taken with the E40, the second with the T420, and then the third, or the one on the far right, with the SC8000. And instead of capturing this target at 0.4 meters or 400 millimeters, I now adjusted my distance to target to the minimum working distance. So I got as close to the target as I could and keep focus. And you can see how the images have improved dramatically by shortening or decreasing my distance to the target. My instantaneous field of views, they stayed the same as they were in the previous exercises. My spot sizes, though, changed dramatically because remember, my spot size depends upon the instantaneous field of view and also the minimum working distance. And my maximum temperatures, as you can see, have gone up as I've decreased that distance to target. Now they are measuring 49.4, 51.3, and I'm not sure why my SE8000 temperature isn't displaying, but it too measures in at around 51. So my temperature reporting capabilities improves dramatically as I get in closer to that target of interest. I would like to review now some of the different optic options that are available for the different cameras. For the E40 system, we have the 45-degree lens optional optic. In fact, that lens comes standard with the E40 camera as part of the Benchtop test kit. With the T420, though, we do have some optional close-up optics. And those close-up optics include what's called a 4X lens and a 2X lens. And I've displayed here in this slide the difference in imagery as a result of employing these close-up optics on our target of interest, which is that IC. And I've also displayed the temperature measurement results. So you can see that the temperature measurement results are fairly close, definitely within the accuracy specification for the camera. You can see that the spot sizes vary dramatically for these lenses, and typically with close-up optics, your spot size ratio is set or locked at a given distance. And only at that distance can you measure with the camera. So for example, with the 4X lens, my minimum working distance is 79 millimeters, and my spot size becomes 100 micron. With the 2X lens, my minimum working distance becomes 33 millimeters, and my spot size becomes 50 micron. If you remember from our pixel pitch discussion, the pixel pitch, which is the size of the detector element in this particular camera, the T420, was 25 micron. If you take 25 microns, multiply it by 4, you come out with the 100 micron measurement. If you take 25 microns, multiply that by 2, you come out with the 50 micron spot size. And that's how you determine the spot sizes for those close-up optics. And you can see in the imagery below how much more detail we're able to capture with the close-up lenses. So if you have an application that requires magnification or resolution, spatial resolution beyond 125 micron that comes standard with the T420 Benchtop test kit, you have that capability by adding to it close-up optics. Now again, as a comparison, I thought I would take our most advanced camera system and microscope lens and show you the result from that system. And again, this is the SC8300 camera, which is the HD or megapixel camera. And I've displayed the measurement results here from this camera. You can see with a 1X lens, which has a minimum working distance of 79 millimeters, my spot size is 14 micron. With the 4X lens, my minimum working distance of 33 millimeters will produce a spot size of 3.5 micron. And this image that is displayed here is our IC, or integrated circuit. This is the target of interest that we wanted to measure earlier, that is roughly 3 millimeters by 2 millimeters. And you can see that not only do I see the target and see the temperatures, I start to see the temperature profile, and I can even now see the lettering that is inscribed on the top of this IC. So if your application calls for even better magnification than 50 micron, you can resolve all the way down to 3.5 micron in the infrared spectrum or with a FLIR camera. Well, we did a lot of calculations today, and they're not too difficult to do, but we do have some tools available to you to help simplify the process. We have a field of view calculator that calculates your instantaneous field of views, your horizontal field of view, your vertical field of view, your spot sizes for you. And all that you do with the field of view calculator is simply input parameters that it asked you for, and those are highlighted here in light blue. For example, in this particular display, it's asking for the focal length of the lens, and we've entered 25 millimeters. It's then asked us for the working distance, how far are we from the target, and we put in 3 meters. It also asks, well, what is your target of interest? What is the target that is under test that you want to see? And we said the target we want to see is 5 meters by 5 meters. And the outputs are all displayed below. If you would like a copy of this field of view calculator to aid you in your field of view or spatial calculations, please reach out to your FLIR representative and we will give you this tool. It's actually maintained in an Excel spreadsheet and is available for all of the cameras that are available. Now, in closing, I did want to review briefly the thermal benchtop test kits that I've referred to a couple times today. One of which I referred to as the T420 camera. The kit includes the camera, 2 lenses, and some real-time recording and analysis software that allows you to connect directly to the camera and record in real time. The 45-degree lens that's included with this particular test kit allows you to resolve down to that 125 micron spot size. So you can get very small with this. There are also the optional optics for 100 micron resolution and 50 micron resolution that are available as add-ons to this kit. And the other benchtop test kit that is available is the E40 benchtop test kit. This particular instrument is not compatible with the accessory lenses. However, with the 45-degree lens that comes with this instrument, you can resolve down to 200 micron spot size resolution. And this kit includes another lens, a 25 millimeter lens, for doing more general type imagery, and it also includes the real-time plotting software. This software allows you to record both snapshots and movies and do time versus temperature plotting and other analysis. Now, in summary, let's review what we learned today, what we discussed. Regarding thermocouples and very small targets, there are some limitations. Obviously, some targets are so small that they are smaller than the thermocouple, so I couldn't necessarily apply a thermocouple to them. But if they are large enough that I can apply a thermocouple to them, yet they're still small and have relatively small thermal mass, the thermocouple, as they are designed to draw heat from the target, will act as a heat sink and actually cool our target of interest and may sway our results, our temperature measurement results. Our thermometers are limited by the size that they can resolve. And the best that we could do was about 5 by 5 millimeters before we started to see substantial error in our measurements. But there are also some inherent limitations to thermometers as well, such as target alignment, knowing exactly where you're measuring, and this averaging impact, but also the fact that there is no input for reflected temperature produces some inherent limitations and errors. With regards to the infrared cameras, we saw that we can resolve some fairly small targets. However, it's very important to understand what the spot size is for your particular lens and camera combination, and that the spot size differs or changes depending upon distance. Remembering that the spot size is equal to the IFOV, which is a fixed parameter for a camera and lens combination, multiplied by the distance. The distance is the parameter that varies or changes. But understanding spot size will tell me what an individual pixel element or detector will see. Now, in order to resolve a target, we learned that it's important to have more than just one pixel. And a 3x3 grid will create an array that allows me to have at least one pixel falling squarely on my target of interest. And that will allow me to accurately measure or present a temperature value. One thing that I didn't point out that is built into many of the camera systems, like the E40 and the T420, is that when you use a spot tool on the camera, you'll notice that in the very center of that spot tool, there is a gap or a circle. And if you fill that gap or circle with your target of interest, you're guaranteed to have a 3x3 measurement grid. Finally, we talked about close-up optics. Close-up optics have a fixed working distance and a fixed spot size. And we talked about accessory optics available for the T420 to include a 100 micron lens and a 50 micron lens. And of course, we talked about the extreme measurement and resolution capabilities of an 8300 camera that can take you to 3.5 micron spot size resolution. I do want to point out again that I've listed or shown here the toll-free number tool as well as their website. I've also listed my email address. If you are interested in a copy of the field of view calculator or have a specific application question, feel free to reach out. Thanks, everyone. Thank you, Keith.
Thank you.